as the voltage gain is nothing but the output, this one or this one, depending on we are talking about AV naught, GV naught, or AV or GB, right? To the input voltage, right? In case of AV naught and AV, it will be input at the stage, and in case of GVs, at the input of the amplifier, the V signal, right? So we already write the expression of output voltage with RL and without RL, right? To be used for with RL will be used for this one, these one, and without RL will be used for these ones, right? So it means for this and this AVs, we need to find the input at the stage, input at the amplifier stage. So the voltage across Rn, right? So voltage across Rn will be very simple. You can see V signal, the input AC source can see two resistances in series. One is R signal and another one is Rn, right? Rn. This voltage can see the overall combination of these resistances, which we already have found as Rn, right? This, right? So the voltage across here will be the voltage at the input of your this stage Vin, and this Vin is nothing but just the voltage divided by version of V signal, right? So Rn divided by R signal plus Rn into V signal will be your input voltage, right? And out of this input, this V input will be across this Rn, and this Rn is just the parallel combination of this and 1 plus beta time these resistances, right? So it means this Vi will be here, appearing here, and appearing here at the base to the overall combination of this. Means 1 plus beta time small re plus capital R, right? To this resistance, right? And out of this Vi, VBE is the voltage which will be developing across small r. So it means VBE will be a part of Vi, right? And it can be found by just the voltage divided by Re divided by 1 Re plus Re. Where is 1 plus beta relation? So 1 plus beta relation actually is cancelled out from numerator to denominator, right? So VBE is the part of Vi, right? Or VBE can be written in the form of V signal, right? If we put value of Vi, this value of Vi here, we can get VBE out of V signal. So what part of the V signal is actually appearing as VBE? So it's a tiny part of V signal as compared to Vi, right? So why we are discussing Vi here separately and we have not discussed in RPi? We had actually discussed that when we said that this was your previous common emitter amplifier without emitter resistance example, right? And at that time we said that this would be your input resistance, the parallel combination of this and this, and you can see whatever voltage here appearing here will be Vin, right? V voltage at the input of your stage, right? And at that time we did not give this voltage as name as Vi. Why? And we actually explicitly said that this statement there, but now I am repeating here that this Vi will be across Rin, right? And Rin is the parallel combination of this discrete RB, parallel combination of R1, RB1 and RB2, right? And R pi, because both these resistances are in parallel, right? Rn is actually the parallel combination of this and this. And the parallel combination volt resistances have the same voltage. So Vi will be here and Vi will be here. And it means Vi equal to V pi. So instead of giving the name at the input of this stage as Vi, we actually named it as V pi, right? And that's why we wrote this equation. V pi is equal to R signal, Rn divided by R signal plus Rn into V signal, right? But actually at that time Vi is actually equal to V pi. That's why we did not give Vi a separate name Vi, right? And this V pi is nothing but VBE, right? VBE, V pi is actually VBE. But now here VBE is a part of Vi, right? Because Vi is actually equal to the still the parallel combination of RB, but with the another one a series combination of discrete Re and your internal base to emitter resistance, right? So now we are ready to write the equations for the gains, right? So let's consider the gain AV naught. So AV naught will be equal to the output at the stage excluding RL. So it means you are actually considering this output voltage, right? So we actually wrote it down here, and ratio of this output voltage with the input of the stage, right? Vin will be your AV naught, right? So, but here we have VBE, but we know the relation between VBE and VI here. So we can put this here to get VI relation with the Vout instead of VB, right? So when we bring it down here, V out by V in is actually equal to minus GM RE divided by RE plus discrete RE into R naught. This one, and this is nothing but your AV naught, right? And its value when we put all these parameters in this equation, we we get 1.66, right? It's very low as compared to our previous example. That's what was in hundreds, but now it's only just still amplifying, but 0.66, 66% is actually amplifying, right? And you have to find AV yourself. So for AV, all these things will be the same, just R naught will be replaced with R naught parallel to RL, RC parallel to RL, right? This R naught is RC. So it means 5K parallel to RL is 5K given in the initial slides. So 5K, 5K, 2.5K. It means your gain is reduced by half. This AV will be reduced by half for this RL, right? So you have to find it yourself. Now let's find out the value of GV naught. So GV naught is output voltage again here at the output of the stage, not including RL, right? So we actually had to consider the same V out relation up to here excluding RL, and but GV naught will be equal to the output voltage at the stage to the input of the source, signal source, right? So it means we need to replace this VBE so that V signal comes here. So we already have this relation, right? Or we can put this and then this, but we already did this step here. So by using this exercise, we can put it here. Then we got minus GM RE divided by RE plus discrete RE, RE divided by R signal plus RE into V signal, right? Instead of VB. So it means V out by V signal, you can find it here. So V out by V signal will be equal to all of these things and R naught. V signal is already gone down here. So this will be your GV naught. And when we put all these values, this is the overall voltage gain of your amplifier overall voltage gain excluding RL. So that's why it is GV not, not GV. Actually, GV usually we named it as overall voltage gain. So GV you have to find yourself. What you have to do, you have to do just replace this R naught with R naught parallel to RL. So it means 5K parallel to 5K, 2.5K will be here. So it means your gain will be reduced to half, right? For GV. So GV you have to find out by yourself. So this is all about the gain cal calculation. So our post problem is solved, but let me explain you one thing that in the book, actually before the book before this discussion, we when we introduced the pi model and t models, we actually said that this is the modeled current source, the voltage controlled current source. Whatever voltage is here, multiply by Gm will be the current source at the collector, right? And this is nothing but I see AC current in the collector, right? At the collector. And this AC current at the collector will be equal to beta IB or GMVBE or alpha IE, right? So T model and pi model are actually giving you twice. One with explicitly writing the collector current to be GMVBE and one with explicitly writing the collector current as alpha IE, right? So no difference, because when we find VBE, then GMVBE will be your collector current. When we have VBE, so VBE is equal to IERE. So IE is equal to VBE upon RE. So IE, VBE and RE are having Ohm's relation. So when you have VBE, multiply it with GM to get collector current. When you have IE through this resistance, just multiply with alpha to get collector current. So this and this parameter is same. So that's what I proved it for you. So GMVBE, put it here, and then I can translate it to alpha IE by writing the basic relations of GM is IC by VT and VB is equal to, by the Ohm's law, VBE is equal to IERE, IERE, right? And RE is equal to VT by IE, right? And IC equals to what? Alpha IE, right? So same DC currents. So please don't confuse with AC and DC currents, right? So now you can see VT VT cancel, IE IE cancel, alpha IE. It means these two things actually have is are the value of the same quantity, which is the AC collector current. Same is done here. You can use this alpha IE and prove it to be equal to GMVB, right? So alpha here IE is equal to, again Ohm's law, VBE is equal to IERE. So IE is equal to VBE upon RE, right? And remember R pi equals to Vt by Ib or beta by Gm, and Re is equal to Vt by Ie equals to alpha by Gm, right? So here I am using Re is equal to alpha by Gm relation. So when I put Re equal to alpha by Gm, so Gm comes up, alpha alpha cancel, Gm VB. It means these two models are the same. So in the book, when you see such a kind of these problems we did here, so you can not be confused when you actually use their method of finding this AV not AV, GV not GV. That relation will equally work, right? The relation can be a little bit, seems to be little bit different, but that will not be different than this one, because they used alpha IE IER, right? So both of these things are same. When you put all the values, you will get the same results. Or again, as I did, I replaced alpha IE by this one. So in their relation, if you replace this with this one, you will get the same relations, right? as we obtain